Number Theory, Section 4, Diophantine Equations. Video 2, Pythagorean Triples. You're probably familiar with Pythagoras' theorem, which relates the three sides of a right-angled triangle A, B and C with the equation a squared plus b squared equals c squared. A Pythagorean triple is simply any set of positive integers a, b and c that satisfy that relationship. So three positive integers that could be the sides of a right-angled triangle. The most famous example of this is 3, 4 and 5. So 3 squared is 9, 4 squared is 16, and 9 plus 16 equals 25, which is 5 squared. If I double each of those values, I get 6, 8, 10. 36 plus 64 gives me 100, which is 10 squared. You might also have come across before 5, 12, 13, 25 plus 144 is 169, which is 13 squared. And slightly less well known, 7, 24 and 25 are related because 49 plus 576 gives me 625. Now, of these, some of them are examples of primitive Pythagorean triples. So a primitive Pythagorean triple is when a, b and c do not share a common factor. So 3, 4 and 5, no common factors. 5, 12 and 13, no common factors. 7, 24 and 25, no common factors. They are all primitive Pythagorean triples. 6, 8, 10 is not a primitive triple because 6, 8 and 10 are all even numbers, so they share a common factor. Let's have a look at an example then. We're invited to write a program to find all the Pythagorean triples a, b and c with a and b less than 25, and then we're invited to show that in every Pythagorean triple at least one of a and b is a multiple of 3. So let's start with what the program might look like. We begin by defining a function called Pythag, which takes a value n. So we're going to find all the Pythagorean triples up to n. So we're going to put in n equals 25 to test our example for this question. And then we look in the range from 1 to n plus 1 and from I to n plus 1 for examples where the integer part of I squared plus j squared square rooted is the same as I squared plus j squared square rooted. So that's saying that I squared plus j squared square rooted gives me a whole number. And if it finds an example where this is the case, the program is going to print out I and j, and then it's going to print out the integer part of I squared plus j squared square rooted. So here's my function, the Pythag of n. Let's try it out with the Pythag of 25. So looking for all of the Pythagorean triples with a and b up to 25. And there it's given me a list. So 3, 4, 5, 5, 12, 13, 6, 8, 10, 7, 24, 25, the ones that we've already seen. And it's found some more examples as well. Now the next part of the question asked us to show that in every Pythagorean triple, at least one of a and b is a multiple of 3. So it might be a good idea here to consider the squares mod 3. So if I'm working mod 3, there are only 3 values to consider. N equals 0, n equals 1, and n equals 2. So 0 squared is just 0, 1 squared is 1, and 2 squared, 2 times 2 is 4, which is congruent to 1 mod 3. Now, suppose that neither a nor b is a multiple of 3. Then I would get that a squared plus b squared would be 1 plus 1, which would be 2 mod 3. But there aren't any squares that are 2 mod 3, so c squared can't possibly be 2 mod 3. Therefore, if a squared plus b squared equals c squared, then at least one of a and b must be a multiple of 3. Let's look at that written out a little bit neatly. So, considering the squares mod 3, we get that 0 squared is 0, 1 squared is 1, and 2 squared is also 1 mod 3. If neither a nor b is a multiple of 3, then a squared plus b squared would be congruent to 2 mod 3, but there is no square congruent to 2 mod 3, so a squared plus b squared cannot be equal to c squared. Therefore, if a squared plus b squared equals c squared, at least one of a and b is a multiple of 3. In this video, you've learnt the definition of a Pythagorean triple, the definition of a primitive Pythagorean triple, and how to find Pythagorean triples in Python.